Hello there. In this video, we're going to continue our discussion of the base points of different integral operators. In particular, we're going to be looking at the Riemann-Liouville integral operator and the Grunwald-Litnikov differential operator. We're going to be discussing or continue our discussion on the effect of our base points, pretty much what they mean, how they sort of change the results of the function under some particular order alpha, and pretty much, continue our discussion of why um, base points create sort of a complicated issue when we're trying to construct a more appropriate or a good choice for a differintegral operator. So I believe talking about exponential functions is of great importance because we know that the function e to the x is an eigenfunction for the classical differential operator. So if it's a eigenfunction for the differential operator of integer orders, then possibly it should have some special properties in regards to fractional order derivatives and integrals, right? So we're going to consider the Grunwald-Litnikov derivative of order alpha with base point a of x of the function e to the x. So if we use the definition that we have here, we can easily find that this is just going to be equal to e to the x multiplied by the limit as n goes to infinity of n divided by x minus a to the power of alpha times the finite sum from L is equal to 0 to n of minus 1 to L gamma alpha plus 1 divided by gamma alpha plus 1 minus L times L factorial times e to the power minus L over n times x minus a. Right? And we can look at this from a different point, right? Because as n goes to infinity, we know that h is going to go to 0 from the right-hand side, assuming we're defining h to be equal to x minus a divided by n, right? So that's our h that is obvious from the classical limit definition of the normal derivative. So we can define this expression here, right? We can define this as some function e with some parameter h of x with some other parameter a. So therefore, the Grunwald-Litnikov derivative with base points ax of alpha of e to the x is just going to be equal to e to the x times this new function ehx with parameter a. Right? So this is our result. So we know, at least from basic calculus, that the derivative of e to the x is going to be equal to e to the x, and this is actually true for all orders k, right? Where k is a natural number. So that's very easy to prove. So we would like, possibly, that this is going to be true for all alpha in the set of positive reals, right? We would like. So is this true? So the only way that is true is if, so this is true if the limit as h approaches 0 from the right-hand side of e subscript h x with parameter a is equal to 1, right? Now, is this going to be true for all base points a, right? Right. So this is true for all base points a. So let us sort of investigate this expression. So as sort of an experiment, I'm going to choose a particular order alpha, and I'm going to look at, so example, let's consider the Grunwald-Litnikov derivative of order 3 with base point ax of e to the x, right? So I'm going to call this function g. So ideally we want g of x to be equal to e to the x, right? So I'm going to look at a few base points. So I'm just going to go over to Matlab, write up a quick script so I don't have to calculate these series by hand. Alright, so let me just give you a quick run through of what I've written here. So I've just created a basic Matlab script. The order alpha that I'm going to be looking at is 3. I'm going to be varying my base point a, so we can start off at 0 for whatever reason, we can increase n since n is going to infinity. Our function of interest is going to be e to the x. And then we can create a vector x over the domain of interest that we want to look at. And then we have our sum. So this is the Grunwald-Lindnikov derivative, where the last part that leads in front of the sum is multiplied at the end after we do our finite summation. So then after that, I'm going to graph the output of this function. So yy is going to be the graph of yy versus xx is going to be the graph of the third Grunwald-Lindnikov derivative of e to the x with base point a is equal to, in this case, 0. At least it's going to be an approximation because we are letting n is equal to 100, not infinity, but we should get the basic idea of what is going on here. So let's just give this a quick run through. And we get this type of structure. It definitely appears to be relatively exponential, so that's not that big of a deal. So let's just vary our base point a. Let's choose our base point to be, say, 10, and let's see what kind of result we get. So again, we get another exponential. It doesn't grow quite as large for 10, but it appears to be at least relatively exponential. But is this truly an exponential curve? So we can choose our base point to be something relatively large if we want, just to see what happens. And as we see at the point 0, it definitely looks to be approximately equal to 0, right? Which I guess is relatively okay. But clearly, if we let our base point be equal to 0 and we run that, then when x is equal to 0, it's clearly not equal to, well, it's possibly equal to 1, since we're looking at a scale of times 10 to the fourth. So how can we test to see if this function is truly an exponential function? So let's just do a quick review on how to sort of transform data points. So the question that we seek to answer now is, question, is g of x an exponential function? At least for a not equal to minus infinity, right? Because we already verified that at least for the Riemann-Liouville, which is equivalent to the GL just in the opposite direction, that will generate a truly exponential function with the properties that we want, right? So our question is, does this operator equal to something that looks like c times a to the bx, right? Does it have this exponential behavior? So if so, then if we take the natural log of this expression, so the natural log of the GL derivative of ax3 ex, that's just going to be equal to the natural log of cabx, right? By properties of logarithms, just going to be equal to the natural log of c plus the natural log of a to the power of bx. We can bring our x down and leave the b there. And then we're just going to have this is going to be equal to, let's see, that's going to be the natural log of a to the power of b multiplied by x plus the natural log of c, right? And this we can call, say, m, this we can call, say, b, and of course this is our y equals mx plus b form, which is a linear function, right? So this is going to be an exponential function if and only if the logarithm of the Grunwald-Lindnikov derivative output is going to be linear. So we can easily go to Matlab, take the log of yy, and see what that gives us. Alright, so if we take a look at the logarithmic transformation of the Grunwald-Lindnikov derivative of order 3 at base point negative 200, we see that this line is pretty much, at least it appears to be a linear function. Now notice that we are graphing on the interval minus 10 to 10, so I'm going to choose a base point in between here so that we can actually sort of see what is going on near the base points. Because remember, when we were talking about the differintegral of, say, sine and cosine, we notice that as we get away from the base point, we pretty much get the behavior we want, but when we're near the base point, it definitely exhibits some unusual behavior. So I'm going to choose a base point, say at a is equal to -5, to sort of get an idea of what is going on there. So notice when we choose a base point of -5, we definitely get some unstable behavior, right? And you can look at the algebraic representation of the Grunwald-Lineikau derivative when a is equal to -5 and sort of get an idea of what is going on there. But we definitely get some unstable behavior near that base point. And we can, of course, shift that to 0, and we can get pretty much equivalent nonsense, I guess if you may. So clearly, unless the base point is either infinity or negative infinity, because we can definitely choose base point, say at 9, it's definitely going to have some nonsense there. But if it's at plus or minus infinity, then we won't really have those issues. And it's pretty much, since minus infinity is not a finite number, same for the positive side, then we're not going to have any nonsense near the finite numbers for which we sort of deal with, right? So with this analysis, we can get the following conclusion. So therefore, if a is not equal to plus or minus infinity, then the GL, moreover the Riemann-Liouville differintegral of exponentials are not exponentials. Right, because exponentials are continuous everywhere, but if I choose a base point that is finite, then we have some unstable behavior or discontinuous behavior at that point, right? And of course, recall, at least for the Riemann-Liouville property that we proved before, that this is going to be equal to e to the x, and this is true for all alpha in the positive reals, right? And that's if we choose a base point minus infinity. If you do not choose minus infinity or plus infinity, then you will not get an exponential function in that case. Alright, so we have that property, which can be a little bit troubling to some people. So let's look at a couple other functions that may or may not give us properties that we want. So example, let us consider the Riemann-Liouville fractional integral with base point minus infinity x of order a of e to the eta x. So we've already proven that this is going to be equal to e to the eta x divided by eta to the power of alpha, provided that eta is a positive number, right? So if I choose some points, let's choose, say, alpha is equal to 1/2 for our order, and let's choose eta to be equal to -1. So let's sort of break the rules that we have here. So if this is the case, then that means we're going to have this is going to be equal to e to the minus x divided by -1 to the power of 1/2, which is clearly equal to minus I e to the minus x. So we cannot clearly extend this definition to negative values of eta, even though this is relatively nice, I guess you could say it, and from an algebraic perspective, right? But this belongs to the complex plane, so that's a little bit problematic. Because if x is a real number, we would ideally like our fractional change to be some real number as well. So clearly, this operator does not give us the result that we would like of the function e to the minus x. So possibly we need to investigate, okay, is there another base point a that is not negative infinity that will give us what we want? So let us investigate the Riemann-Liouville integral with base point ax of order alpha of e to the minus x, and let's see if there's an operator that will give us what we want for this. So we know this is going to be equal to 1 divided by gamma alpha times the integral from a to x of x minus t to the alpha minus 1 times e to the minus t dt, right? So what do we know about e to the minus x? So we know that e to the minus x is bounded below by y is equal to 0 on the right-hand side of its domain, right? So possibly, at least as an educated guess, maybe a to be equal to infinity will do. Maybe, right? So minus infinity gives us our bounded nature for e to the x, so maybe positive infinity will give us our bounded nature for our Riemann-Liouville differential operator of e to the minus x. So let's give that a try, and let's see if that gives us what we want. So we get RL infinity ix alpha of e to the minus x is going to be equal to 1 divided by gamma alpha, the integral from positive infinity to x of x minus t alpha minus 1 e to the minus t dt. And we can perform some operations here, so we can let u be equal to x minus t and shift everything as normal. So once we do that, we're going to get this is going to be equal to minus 1 divided by gamma alpha times the integral from minus infinity to 0 of u to the alpha minus 1 times e to the u times e to the minus x du. So with that being said, we can sort of pull out our minus 1 and our e to the minus x, because that is our intuitive antiderivative of e to the minus x, right? So I'm going to group that together and look at everything else separately. So I'm going to have minus e to the minus x, and then I'm going to multiply that by 1 divided by gamma alpha, integral from minus infinity to 0 of u to the alpha minus 1 e to the u du. So what do we have here? So this is almost like a left-sided Laplace transform, so we can easily mirror that to the other side if we want. So transforming that domain, we're going to get this is equal to minus e to the minus x multiplied by 1 over gamma alpha times, let's see here, so this is going to be equal to the integral from 0 to infinity of minus 1 to the power alpha minus 1 t to the power of alpha minus 1 e to the minus t dt, right? Let's see here. So what do we have? So this is going to be equal to, so I can pull this minus 1 alpha minus 1 out, so we have minus e to the minus x times minus 1 to the power of alpha minus 1. Now that's could be complex, like if I choose alpha to be equal to 3 halves, that's going to give us I. And then we have times 1 over gamma alpha times the integral from 0 to infinity of t to the alpha minus 1 e to minus t dt. So we know this precisely is equal to gamma alpha. So gamma alpha over gamma alpha will cancel. So therefore we have what? So therefore the Riemann-Liouville with base point infinity of ix of alpha of e to the minus x is equal to the standard e to the minus x, but we have this minus 1 alpha minus 1 term there, right? So, that seems to be okay. We can test it on our integer cases if we want. For example, if I choose, let's just choose 1. So the antiderivative of e to the minus x, we can find that that's going to be equal to, so that means we're choosing alpha to be 1. So 1 minus 1 is 0, that term cancels, so we're just left with that, right? And let's see here. So we have that property, and we also have this property, right? So both of these properties checks out to give us properties that we want, right? So when we're dealing with e to the x, we're going to choose base point minus infinity. When we're dealing with e to the minus x, we're going to choose base point infinity. At least that gives us what we want in terms of the classical derivative. Alright, so let's see if we can be a little bit clever here. So notice infinity is associated with a constant eta is equal to minus 1, and minus infinity is associated to a constant of positive 1. So what if we sort of go down the middle and play around a little bit? So what if I choose the Riemann-Liouville with base point 0 of x of 1? Now let's consider e to the 0x, right? So is this going to be equal to 1? Take a guess. So we know, at least this operator works well on functions of the form x to the nu, right? So we know that the Riemann-Liouville basepoint 0 differential operator of order alpha of x to nu is going to be equal to gamma of nu plus 1 over gamma nu plus 1 plus alpha times x to the nu plus alpha, right? So here I'm just going to choose alpha to be equal to 1, nu to be equal to 0, right? So in that case, that's going to give me gamma 1 over gamma 2 times x to the positive 1, which is of course equal to x, right? So clearly that's not equal, so therefore this proposition is false, right? So the reason I bring this up is some people try and jump to patterns a little bit too early in the game. Definitely not try to do so, right? So what is the conclusion of this base point discussion? So when dealing with the Riemann-Liouville differintegral or the Grunwald-Lendnikov derivative, right? Choosing base points will give different results. Most of which are different. From, for example, ik and dk, where k is a natural number, so the classical integrals and derivatives from standard calculus. So if that is the case, then we have an issue, right? So we have an issue with Riemann-Liouville and Grunwald-Lendnikov derivative, because then we have to sort of, deal with base points, right? So we know base point 0 works well with polynomials, base points minus infinity works well with sine, cosine, and exponentials. So when we start solving, say, fractional differential equations, let us assume I have, say, the half derivative of u is equal to, I don't know, e to the minus x plus x squared, right? So how will I deal with this problem, right? So let's assume that this is a base point, say, minus infinity, right? And let's assume that this is the Grunwald-Lendnikov derivative of base point x, right? So we're solving this equation for u. So clearly, what I want to do is apply the inverse of that, right? So I'm going to take the Riemann-Liouville order of 1/2 with base point minus infinity of x of GLD 1/2 minus infinity of xu, right? That's just going to give me u. So then I'm going to have my Riemann-Liouville fractional integral with base point infinity of e to the minus x plus x squared, right? So we know that this, as we've already discussed, is going to be equal to minus e to the minus x, but this piece right here, so Riemann-Liouville of order 1/2 of x squared is not going to be the normal extension of the power rule, right? Because we know the power rule only applies or is extended continuously if the base point is equal to 0, right? So this piece behaves nicely, this piece doesn't. And the same thing can be said if I change these two numbers to say 0, right? Then the polynomial part is going to work great, and the exponential is not going to give us exactly what we want, because remember, RL and GL of exponentials are not exponentials unless the base points are plus or minus infinity, right? So RL and GL are going to really be an issue when we start working with fractional differential equations, right? So just keep these things in mind as we start to build new alternatives towards generalized fractional derivatives and fractional integrals. Hope you enjoyed.